Welcome back everyone, this is chapter 7 of the Advanced SQL course. So it has come to this, we are inching towards the final videos of this entire course. I think this will be the second to last video and I would like to spend the next few minutes on a bigger use case, on a bigger application that binds all of the techniques together that we have discussed in this course. There will be bits of pure SQL of course, but there will also be recursive CTEs. There will be advanced data types like JSON, for example, and everything will play nicely together to implement a non-trivial and interesting sample application, I hope. Well, the sun is setting behind me at Tatooine, and well, this course is coming to an end, and I hope that well, everything together gives you a coherent picture of how advanced SQL can taste. So let's dive right into this application, and let's discuss this here, and then have one final video to say farewell and then tie everything together. So let's go. Alright, so the application I would like to discuss with you is the core of a very simple spreadsheet application. You all have used Excel or Google Sheets like spreadsheet applications where you are faced with rectangular grids in which each of the cells of these grids can be addressed or referenced by a letter number combination. So let's see, this particular cell in which we have the 6.10 stored here, this particular cell, well, that would be addressed using the column and the row identifiers here. So that would be cell B2. All right, so in cell B2 we have this numeral here, and we have further numerals as you can see in other cells. For example, in A3 we've stored the 2 here, but there are cells of a different type, cells that don't contain literal values, but they contain formulae. So that would be a multiplication formula that references two cells A1 and B1. Okay, so this is A1 and B1, 1 and 3.5. The multiplication of this would be 3.5, and that would be the value of cell C1. We have to evaluate the cell to obtain its value 3.5. And of course, all of the formulae would have to be evaluated here. So this would probably result in 2 times 6.1, that's 12.2, and that would be the value of cell C2. We could evaluate this cell here and would obtain more literal values, all right? Once we have obtained all of these literal values in column C here, we would be ready to evaluate this particular formula. It's an aggregate, and I think you can guess the semantics of that. We would just sum up all the values that have been collected here in the C column, and then derive the sum aggregate and place it in column C4. There's another sum aggregate here, and that would define all the values in the ABC columns. Right, so the last interesting bit would be this formula on the bottom right here. This references D1 and C4. D1 is just literal value, no problem about that. C4 references this aggregate value. Well, luckily we have just computed its value and would be able to then also evaluate this final formula here. And taken together, all of these evaluations would lead to this particular form of our spreadsheet, in which all of the cells, all of the non-empty cells, let's say, carry the literal values that describe their value. We have summed up the number of items here in the A column. We have summed up the number of, well, whatever invoice positions here in the C column, and we were able to derive this total value of the invoice in British pounds that we could compute by taking this euro value and multiply it with the, well, with the conversion factor that's currently in charge. It's stored here in cell D1. All right, so we end up, after evaluation, we end up with a sheet that only carries literal values. Formula have all been evaluated. All right, so that would be our goal, to implement a representation, a relational tabular representation of such spreadsheets that contain formula in different cells, and then have a routine, of course, database SQL implemented routines that convert this spreadsheet into its evaluated form, in which all of the cells carry literal values only. All right, so that's quite an interesting task, I would say, because some nice algorithmic aspects play into this. Also, some interesting questions about the representation of data, and all of this can be answered by using the techniques that we have assembled and collected over the recent weeks. Okay, so well, what you see here in this in these spreadsheets are, next to formula in blue, you also see parts of static text that is present here in the spreadsheet to make the output more readable. We will not represent the static text here, that's easily added, so we will focus on the blue parts, on the blue bits here, on the values and the formulae that populate these spreadsheets. Well, as I walked you through the evaluation of this particular spreadsheet, you already saw that there was a non-arbitrary order in which I did that. So I made sure, before I evaluated this particular sum here, I made sure that all the evaluations in the C column that this sum references have already been performed. To perform this particular multiplication, we had to reference other cells, A1 and B1. Well, luckily, they carried literal values already. But there is a dependency of formula on other cells or other formula. All right, so there is a dependencies, and we have to take care to evaluate these formula in the correct dependency order. Evaluating this particular aggregate here before we have evaluated all these multiplications will be will probably lead to an error. We have to take formula dependencies into account. That would be the first step that we undertake here. All right, so what we will thus extract from such a given spreadsheet with formula, we will extract a dependency graph that will probably look like this. This is a directed graph in which each of the nodes represent a single cell in our spreadsheet. Such an edge here indicates that one cell uses or references another. All right, so let's see. Let's look at D4 here. D4 references D1 and C4. Okay, let's check in the spreadsheet. In the unevaluated spreadsheet, indeed, the formula in D4 references D1 and C4. And this is exactly what we see here. D4 references D1 and C4. Before we can evaluate D4, we have to evaluate D1 and we have to evaluate D4, which of course requires that we have evaluated C1, C2 and C3 before. C4 is indeed the sum aggregate that references all the values in the C columns. These are the multiplications, and they can only be evaluated if the arguments of these multiplications have already been evaluated. All right, so there's a transitive dependency order, a uses or a reference order that is described by this directed acyclic graph. All right, there are some cells here, for example, the B1, A1, all of these in this particular row, and also the D1 cell, that do not depend on any other cell. Well, they probably contain literal values already. So that would be where we could start our evaluation, in cells that do not depend on each other, on other cells. These cells would stand on their own with their literal value, and that would be the start of our evaluation procedure. Once we've done that, once we know B1 and A1, and it's easy to know these because they do not refer to anything else, we could evaluate C1. Likewise, we could evaluate C2 and C3. And once we have all of these, well, we could evaluate C4. And only in the very last step, we could evaluate D4. D4 would be the last cell that has to be evaluated here. So given this particular dependency graph, we would need some logic that would derive a valid evaluation order for all of our cells. And well, deriving such an evaluation order would be easily done using a topological sort on this dependency graph. This is a directed cyclic graph. Cycles in this graph would indicate that the evaluation of one cell recursively relies on its own evaluation, which would constitute a real problem in our setup here. But this is not the case in this graph. It won't be the case for any spreadsheet that we consider. We can topological sort this DAG and thus derive a valid evaluation order in which probably all of these cells in this particular row would come first, including D1, and in that order would D4 would come last. All right. Well, this is a task for a recursive common table expression, I would say. Given a representation of this dependency graph in a simple two-column cell here, in a simple two-column table, in a simple two-column table, well, we could use the following recursive CTE to compute the topological sort of the thing. All right, so let's see how we would do that. So we are given the dependencies table. This cell uses this other cell. All right. We would start this topological sorting by finding all those cells that are being used or referenced, but themselves have no further references. These are the leaves of our DAG. And this is exactly what we are doing in this particular first query of our, here we are, of our recursive CTE. So let's find all the cells that are being used, but do not use other cells. All right, so these are the leaves of our dependency graph, and we would record them with a position 0. This position reflects the time at which we can evaluate these particular cells, and indeed we could evaluate them at the earliest possible time at time 0 here. All right, so that would be all the leaves of the dependency graph. In the recursive part of our CTE, which is here, we of course refer to the dependencies that we were given and all the earliest evaluation times that we have already found. So a cell that uses another cell e.cell which can evaluate it at time e.pos, well, this cell D has to be evaluated at the time after e.pos, and this is exactly what is expressed here. E.pos plus 1, that would be a possible evaluation time for the cell D here, and this is the next entry that we would record in our earliest pos cell CTE. In this common table, we could find that a particular cell could be evaluated earliest at this particular point in time, at the pos point in time. All right. Once we have explored all the references inside this dependency graph, we would not be able to produce any new pos cell tuples here, and the evaluation of this recursive CTE would end. So finally, a topological sort can be derived from our earliest table by just considering for each cell, well, the latest point in time that we have recorded for its possible evaluation. We are looking at the latest point in time because then it's safe that all the dependencies for that particular cell are available now. This would be the safe point in time to consider the evaluation of cell e.cell, and that defines our topological sort. All right, so let's see how that could look like for our sample DAG. This is the dependency DAG of the sample spreadsheet again, and if you evaluate the earliest CTE and the topo sort post-processing CTE on this particular input, well, what you would get is this output table. This is indeed a topological sorting of all the nodes in this dependency graph. As you can see here with possession 0, we find all the leaves of this dependency graph. Of course, all of these cells can be evaluated at the earliest point in time because they have no further uses references. So we find all the nodes here in this particular row, and we also find node D1, which has no further references. Indeed, all of these could be evaluated in parallel at point in time 0, let's say, because they have no particular interdependencies. Well, at point 1, at point in time 1, let's mark this, all right, at point in time 1, all of these cells, A4, C1, C2, C3, all of these could be evaluated now. So A4 refers to A1, A2, A3. All of these have been evaluated at time 0 already. These are the multiplications, C1, C2, C3. They all refer to cells that have already been evaluated at point in time 0. All right, so that looks good to us. And well, then C4 can be evaluated, which is the aggregate over all these multiplications. And well, at the very last point in time, well, we can evaluate the bottom right cell in our spreadsheet, and that's cell D4, and indeed it is found here and in the last position in our topological sort. Right, so this topological sort indeed correctly reflects that there is some opportunity for parallel evaluation here. We could of course simply use a dense rank on this particular column here, on the pos column, to derive a strict sequential order. All right, so if this is of interest to us to have a defined sequential order, then simply use dense rank on the pos column to derive unique points in time where you could evaluate a particular cell. I brought all of this spreadsheet business with me in a sample SQL file here on in the terminal, and so let's see how that looks. All right, so indeed we find a recursive CTE just as mentioned on our slides, and what you will see here is well, the computation of the dependencies table, the two-column dependencies tables whose existence we assumed when we were talking over on the slides. This is proof that we can indeed infer or extract these dependencies tables from the sheet that we were given. We will have a closer look at the sheet, and we will have a closer look at the refs function which extract these references, the dependencies, from the particular given formula in the cells. But for now, let's only have a look at the dependencies table itself. So let's scroll down here and then have a look. Yes, this is indeed configured to simply output the dependencies. So let's see. Okay, there we go. These are the dependencies found in the sample spreadsheet. So indeed, well, we see that, for example, this one particular aggregate, where is the aggregate in C4? Well, the aggregate in C4, indeed, it refers to all the multiplications in the C column. So C4 references C1, it also references C2, and it also references C3. These are all the dependencies that we have extracted. All right. So that should be the dependencies table. It's a 14-row table for this tiny sample spreadsheet. Okay. So, well, what you see here, let me enlarge the code window again. What you see here is just the code from the slides. It's the earliest CTE and the topo sort processing that will compute the overall topological sort that we need for our for the derivation of the evaluation order, of cell evaluation order. So let's see how that result looks like. Let's have a look at the topo sort table, the post-process table, and what we find here is indeed, oh yeah, this is the parallel ordering, evaluation ordering that we have already mentioned. Yeah, so all of these cells could be evaluated first in parallel, and cell D4, in fact, the bottom right cell in the sheet, has to be evaluated last. So that would be an implementation of the topological sort. Now we have evaluation order in place. Well, to do that, to actually do that, to derive this evaluation order, we had to extract the dependencies, and the dependencies, they build on this particular UDF that we have to build, that looking at one particular formula, well, will extract all the references, all the used cells that are mentioned in this particular formula. This is, of course, the basic support that we need to build this dependency graph. Let's tackle that next. Well, before we can do that, we have to have an idea of how to represent the formula themselves. So we would need to have a representation that indeed supports the extractions of these references so that we can build the dependencies graph. And of course, we would have to have a representation that allows for the evaluation of simple arithmetic expressions, for example, of the multiplication of two cell references. And well, we have talked about the representation of such expressions before in the course, and indeed we were using JSON objects to do just that, and I would propose to well, to adopt this particular method here too, and have a spreadsheet representation in which all of the cells carry JSON objects that we use to represent the hierarchical structure of formula. Okay, so well, here's a sample of different formula and how they could be represented using JSON objects. Right, so I think this should be rather self-explanatory. So all of these JSON objects follow a common theme. They are actually represented in two parts. The parts to the left of this line that I've just drawn would indicate which type of expression would be represented by the JSON object. We can represent literal numbers. We can represent cell references, so an expression that refers to another cell. We can represent n-ary operators, and we can represent aggregates like the sum aggregate that was referring to an entire rectangular region of cells that would then be aggregated. All right, these would be the four kinds of formula that we represent. On the right hand side, we would have well, a more detailed description of the type of expression. The detail for a number would only contain that literal number, well, 4.2 maybe. The detail for a cell reference would mention the cell reference, and you can see how we will represent these cell references. They would be just two column pairs or rows with two entries which indicate the column and the row identifier that we use to identify cells. Operators like this binary operator plus, but any n-ary operator would simply be represented by an operator symbol and then an array of arguments to this particular operator. This is a binary operator. This plus would be a binary operator, so we would expect two subformulae that would be held here in this array args. Right, so any n-ary operator, unary, binary, ternary operators, everything could be represented in this particular array-based representation of arguments. And then there is aggregates, which would also be represented by some, well, aggregate symbol. This would be summation, obviously. And then a rectangular array of cells over which we would aggregate. So that would describe the upper left and the bottom right corner of this rectangular area of cells that would be aggregated over. And again, you find our representation of cell references here. Okay, I think this should be easy enough. It's a simple, JSON-based representation that takes into account that expressions may be nested inside each other. So the argument of summation here might be another multiplication, for example, and the cell reference. And all of this could be easily represented by just nesting these JSON objects. Okay, so based on this representation of JSON objects, how would we reference the set of cells that are referenced by a formula? Well, we would write a PL/SQL UDF, for example. Okay, so that PL/SQL UDF would receive an expression, of course, represented as a JSON object, and it would return a table of cells that are being represented or referenced. I'm sorry, referenced in this particular formula. This user-defined data type cell here would just be a pair of row and column identifiers, just like I've already described on the previous slide. We will see the definition of cell when we switch over to the SQL terminal for the next time. All right. So, well, to extract the reference cell from an expression, we would simply inspect the kind of expression that we are currently facing. There are 4 kinds: the op kind, the aggregate kind, the cell and the num kind. We would just tell them apart here using this conditional case expression. Well, and then handle the different cases. In the num case, for example, well, there would be no further references, and well, we would have just this null no op statement expression here that indicates that this is the case that we have handled, but there is no further cell reference to be added to the output table of our set valued refs UDF. In the case of a cell reference, well, it's obvious. Well, of course, there is a cell reference, and this reference cell should be added to the table of cells that are being referenced in our formula. And this is what we do here. To the output table that we are currently accumulating, well, we will add the cell that is being referenced by our current formula. All right. In the case of an aggregate, well, we would simply generate the range of cells between the from and the to, the upper left and the bottom right cells in the rectangular range. All of these cells would be term C, and all of them would be added to our accumulated table of cell references. What you see here is that we used return query so that all the rows returned by this particular query here are being added to the accumulated result table. Of course, we are using this auxiliary function cells here. I can briefly show you how that's behaving on the terminal in a minute. And then there's a case of n-array operators. Such an n-array operator has an array of arguments, all right? So we would just simply access all of these arguments inside the array. This would be the argument array. This is the function that we've already discussed, a set returning function that would simply build a table of all the arguments, of all the elements inside this array. All of these elements would be termed arg, okay? These could be arbitrarily complex expressions again. So we would invoke ourselves, we would invoke the refs function recursively here, and simply collect all the references that are being made by this argument. Let's call these C, and then simply select all of them in this particular query. And all of these collected references, they would be added to the accumulated table of references that we are currently building. So that would be a recursive PL/SQL UDF. Here at this particular point, refs calls itself on sub-expressions of the current top-level expression E. All right. I think also this should be simple enough. So let's switch over to the terminal again. So maybe it's time now to quickly review the representation of our sheet here and the representation of formulas. So, well, this is just user-defined cell type. And as I told you, it's just a pair. It's just a 2-column row type that stores the column and the row information so that we can address cells. Columns are marked A, B, C, D, and so on. So we reference them using a text value. Rows are just numbered from starting from 1, so we can reference them using just a plain integer. Okay, so that would be our representation of the entire sheet, of the entire spreadsheet. Well, it would just be a collection of cell identifiers. Okay, and well, inside these cell identifiers, we would find formula. So as simple as that, a simple 2-column table is sufficient to represent the entire spreadsheet. Right, and then there is the JSON representation of our formula. And while this directly follows the discussion that we just had on the slides. This is an ASCII representation of just the formula content of the spreadsheet that we've seen on the slides already. You see that all the static text has been removed. Everything that's left is formula that have to be evaluated. And well, this is this particular spreadsheet represented in its two-column tabular form with all the cell locations here, the cell addresses, and of course the JSON representation of the formula that are stored in these cells. So let's look at cell C1 here. Cell C1 carries an operator. It's a multiplication operator which has two further arguments. So that would be a two element argument array here, and these arguments are references, are further expressions. In this case, it's simply references to other cells, namely the A1 and the B1 cell inside our spreadsheet. That would be the representation of our sheet and all of the formula. And well, now having a look at the refs function. Here's the refs function. It's just a plain copy of the function that we've just seen on the slides. Of course, it has the recursive invocation of itself, as we've mentioned, as we discussed the function. Well, we could simply exercise that function here using this tiny piece of SQL. Well, what we would do is look at a particular cell inside our spreadsheet S. So let's identify a particular cell here. That's what I'm doing. A2 is the cell in question, right? And well, we of course would use the particular formula in that cell and extract all the cell references that we would find in cell A2. Now, A2 is a very simple cell. It's just a number cell. We don't expect such a number cell to carry further reference to other cells. So I think this should return the empty table. And it does. It's different for the cell C1. This is the binary multiplication operator that we've just discussed. It should contain references to two further cells, the arguments of the multiplication in this particular case. And indeed, we find that the C1 cell is referencing the A1 and the B1 cell. All right. And interesting also could be the let's say the C4 aggregate cell here, which is referring to all the cells in the column C, the C1, the C2, and the C3 cell. And indeed, this is what we find. So our refs function indeed appears to do what we expected it to do. In the case of the aggregate, we were referring to an auxiliary function here that can simply enumerate all the cells that lie in the rectangular region between the upper left from and the bottom right to cell here. Well, I can also exercise this cells function and it will probably behave as you expect. If we enumerate all the cell references inside this A2C4 rectangle, then this is what we will get. Right, so A2, A3, A4, and then the B cells in the middle, C2, C3, C4 would be the final cells in this particular rectangle. If you want to have a closer look at the cells function, it's not particularly exciting. You will find it here in the PL/SQL code that I've distributed in the repository for you. All right, so indeed, we found a representation of formula that lends itself to the extraction of cell references. That's, of course, one crucial characteristic of this representation of formula. Of course, we would also need a representation that is fit for the evaluation, the arithmetic evaluation. And this would be the next topic to consider. So how would we evaluate a particular given formula? So, well, this is the task of the eval function, all right? And the eval function would again receive a formula to evaluate, and once it has performed evaluation, what we will get would be a numeric value, a literal value that we could just enter into the spreadsheet. It's in this case, I've just decided to work with float values here, but we could work with numerics. Probably that would make sense in the context of such spreadsheet evaluation, any type, any numeric type would work here. All right. Well, just like the refs function, the eval function would simply inspect the kind of the expression that is to be evaluated here, and then branch based on the kind of expression and perform its thing. So let's see again. We see this particular case branch here that would inspect the kind of the expression. Let's first look at the very simple cases here. For example, if the expression is indeed very simple and represents just a numeric value, well, then this is all we need. We would just extract that particular numeric value from the JSON object. No further work is to be done, and here we are. That would be the result of the expression evaluation. All right. What about the cell reference? Well, since we have applied topological sorting, we can be sure that any cell that will be referenced, will not contain a complicated expression. It will contain a simple value. All right, and this is what we are doing here. We will simply follow to that reference cell here and extract the value that is being held in this particular cell. There is an auxiliary UDF here value that can do just that. All right, so this is the particular simple case, and we don't need to recursively invoke ourselves here because well, we can count on cells that are being referenced to be already evaluated thanks to the topological ordering. All right, so how about aggregates? Well, aggregates are also very simple to do. We would simply look at all the cells that lie in the range of this particular aggregate. We would call these cells C. We can count on these cells C to be already evaluated thanks to the topological sorting. So what we will do is we will range over all these cells C and we will simply extract their value. These cells cannot contain anything else but simple values, and then aggregate these values. This is, of course, which aggregate we compute is, of course, based on the aggregate symbol that is being represented inside the JSON object. So on summation, we will use the SQL sum aggregate here. And then there's only the case of the n-ary operators that we should consider. So if we indeed find such an n-ary operator, we would look at its particular operator symbol. We will find many operator symbols here, but we may find the plus sign, for example. And in this particular case, we would simply recursively evaluate the argument of this particular operator. It's a binary operator, so it will have the zeros and the first element in the arguments array, and we would recursively invoke ourselves on these particular sub-expressions. Right, and that would already finalize the eval logic. Again, the hierarchical structure of the JSON object lends itself very nicely to a recursive exploration inside this SQL UDF and recursive exploration and evaluation, as you can see here. Okay, so I've already implemented this on, of course, here on the right-hand side, and we could have a closer look at this is the formula, the value auxiliary UDF. Let me scroll by that. It's not particularly interesting, and that would be the eval UDF. Indeed, it receives an expression E, and it will return a float value. All right, so what you see here is just the logic from the slides, but all the cases that we have elided on the slides, they are being listed explicitly here. You see subtraction, multiplication, division, all of this is being handled here explicitly. We also bail out and complain if there are operator symbols inside our JSON expressions that would be unknown to us. We are raising an explicit exception here. Since there is no exception handler in this particular function, that would be escalated to the top level in the end, and the query evaluation would stop with a runtime error that would detail our complaint. So that, for example, that an unknown operator symbol has been found. As you will also see, well, there's all the cases for the different aggregates that we would like to support in our spreadsheet. They have all been listed explicitly here. All right. So that would be the recursive eval function, and well, we of course could exercise that. We could simply look at one particular cell here inside our spreadsheet, for example the A1 cell, and then extract the formula in that particular cell and have it evaluated, and that should work well if there are no further references. If there are no further references to our cells that lead to unevaluated cells, all right? Because we have not described the complete evaluation logic for our sheet here, only those examples will work that evaluate expressions that do not refer to unevaluated cells. So A1 is such a cell, it just contains a single number, and this indeed it probably is the number 1 that is contained in the A1 cell, and we can extract that. We can also evaluate the binary multiplication in cell C1. This refers to cells A1 and B1, but both of these contain simple numbers only, literals only. We can evaluate this. This should work too, or this leads to 3.5. We cannot evaluate C4 yet, which is an aggregate that ranges over the entire C column, but the C column still contains unevaluated multiplications. So we will probably see the eval function complain at this particular point. It assumed that topological sorting has taken care of the evaluation of all referenced cells. This is not the case in the current state of our query here. So well, indeed we get a complaint here that well, we expected a number in cell C1, but there isn't any. Indeed, there isn't any. There is a multiplication that first has to be evaluated before we can evaluate our aggregate. All right, so that would be the eval function, right? So now let's tie everything together. Now let's finalize the entire thing. Let's use the topological sorting, and let's trigger evaluation of the individual cells in our spreadsheet in the correct order. This will tie everything together. So that would be our grand master plan for the evaluation of our spreadsheet. It will be the eval sheet function, and it will be a PL/SQL UDF. So what we will have as ingredients here is, of course, our table sheet here, which is the 2-column table that we've already discussed. It contains cells and the formula inside these cells, which of course will be JSON objects. We will have logic to extract dependencies from these formula using our refs function, and we would use these dependencies to build a topological sorting, topological ordering of the cells. Let's call this topological ordering CS. So what we have discussed at the very beginning of this video, this topological ordering of cells, let's capture that in a sorted array CS. So evaluating the cells in CS order would lead to a valid evaluation order of our spreadsheet. And this is exactly what we will do inside our grand eval sheet function. We would simply iterate over the cells in the CS array, of course in topological order. All right. We would then read the formula E that is being held in this current cell C. We would simply read it off the sheet. We would evaluate this particular formula, and we can be sure that this evaluation will not fail because all the references that will be found in expression E are already being evaluated. All right, so this will lead to a floating point value V here. This is the value of the expression E. To record that, we will perform an update inside our eval sheet. We will have indeed a side effect on the database. We will update our original sheet, our spreadsheet representation, to not contain a formula anymore, but to contain a plain number that of course is equal to v, the just evaluated expression. Right. Once we've done that, once we've performed this loop here inside our eval sheet function, the entire sheet will only contain of literal number entries. Literal number entries that defines the final state, the final evaluation state of our spreadsheet. If you recall our very first slide in this particular video, after evaluation, the entire sheet only contains literal numbers. This is exactly what eval sheet will give us. All right, so let's have a quick look at the pseudo code now, at an excerpt of the eval sheet function. There is a little more to it, only very little more there is to it, to this eval sheet function over in the real code. Otherwise, this would be the core of our entire spreadsheet evaluation, and it still fits a single slide here. I think that's quite remarkable. So what we will receive here in the eval sheet function is indeed an array of cells, the topological order of cells that we will consider during cell evaluation. And we will return a boolean that indicates whether the evaluation went okay. I really expect this boolean to always be true, actually. Right. Well, let's do that. Let's simply iterate over all the cells that have to be evaluated in our spreadsheet in topological order. And well, if we do this for each iteration here in our SQL code, then indeed we will visit the elements of the CS array in order, and all of these elements will be called C. These are the cells to be evaluated. We will simply look up the formula inside cell C here. This is just a simple select into here from the sheet. E will be that formula. We will evaluate that formula. We will receive a value V and then update our sheet. We will update our sheet in exactly the cell C that we are currently considering. And the new contents of that cell C won't be a formula anymore. It will be simply a plain number entry. It will be a JSON object that we have defined, well, that defines a literal number of value V here. All right, and that would be the core of our spreadsheet evaluation. Let's switch over to the terminal one last time to see that in action. So this would be the eval sheet function here. It indeed follows the code that you have seen on the slides. As I told you, there's little more here. We would, for example, complain if there are references to cells that we indeed cannot find inside our spreadsheet. But all of this is just for our own sanity. This should not happen at all, actually. Right. Okay. So, well, if we can find the formula E, then we evaluate it and we indeed update the sheet here. So that would indeed be a PL SQL UDF that performs side effects on the underlying database, in this case, our spreadsheet. Right. Okay. So let's just do that. Let's perform sheet evaluation. So sheet evaluation would, of course, start with dependency computation. All right. And then once we've done that, let me deactivate the topological sort here. Well, and once we've done that, well, we would simply consider the topological sort output here. We would arrange the cells of the spreadsheet in topological order. This is done by this array aggregate. And exactly this is the input to our eval sheet function. All right, so let's do that. Take some time is also due to the video encoding that the laptop is currently performing, but we are done. The eval sheet function indeed returns with the true here. The evaluation went fine. The sheet itself, the evaluated sheet itself, of course, is found in the original sheet table that now has been updated. So let's have a look at that sheet table. Okay, it contains all the entries here. And indeed, all the entries are now filled with, well, simple numeric literals, which represents the state of our sheet after evaluation. Evaluation is complete. This is the bottom right cell, D4, 15.5408, just like on the slide that we've seen, would be the result of this evaluation. All right, so I hope that you could enjoy this particular use case, because it really collected together, bound together all the techniques that we have discussed during the most recent videos. I can only invite you to have a closer look at the PL SQL code and the SQL code that will be found in the spreadsheet.sql file. I think there are some quite interesting techniques in there, and it gives some impression of how much computation you can actually do right inside the database. No need for a separate spreadsheet or evaluation routine outside the realm of the database here. This can all be done inside the database. And of course, this is super simplistic, so that we can fit it into a 50-minute video, but building on that and building a richer spreadsheet implementation in SQL should indeed be doable. All right, so this is almost the last video in our advanced SQL course. There are some more notes on PL SQL and the performance of PL SQL, but let's postpone that for the last video. I hope to see you there for this final bit of advanced SQL. See you then. Bye.